So our next talk is Kristen from Illumina. Christian from Illumina. So she'll talk about the technology aspect of genetic analysis.
Hello everyone, my name is Christine. I am the Illumina Territory Account Manager that covers the academic side of the University of Michigan. I'm joined here today by my colleague Jeff. He covers the clinical side, as well as Rebecca, who is our district sales manager. Today I'm giving you a very brief, quick 10-minute snippet on some of the new arrays and updates to sequencing that we have here at Illumina. So buckle up, it's going to be kind of quick, really good information. But if you have any questions at the end, we'll have our emails up there. Again, it's going to be quite fast, but it'll be good information. So first, many of you in this room might be familiar with the Infinium arrays. So if you've ever heard of the Global Diversity Array, the Asian Screening Array, the Methylation Epic Array, a lot of those are built around our Infinium technology. To date, we've had over 100 million samples that have been utilizing this type of array. It's very accurate. As we all know here at MGI, it's very scalable, reproducible, and one of the most cost-effective methods for getting some genotyping. But what's new is what we call our Excalibur or EX platform. This platform is quite amazing in terms of the innovation and its ability to be automated, to be quicker. So turnaround time, these 48 sample chips allow up to, I think, 600,000 samples a year on just one iScan system. We also have software compatibility with what we call our Dragon Array and our Clarity LIMS system. Dragon Array is actually relatively new within the last year. We're trying to add our methylation arrays. We have PGX analysis, PRS analysis on top of it. We actually have two professors in this room, one who's piloting the local version and another one who's moving forward with some of his samples as well. So if you have any questions, with their permission, if I can share their names, I'd be happy to give you their information and they can tell you what they think about our software as well. Again, looking at the Dragon Array, we can do genotyping, we can do SNP analysis, we can do star allele calling, whatever you want. We're trying to develop it, so we'd love some feedback on this. One of the things I do want to note is we do have a local version, because I know when it comes to data security, that's very important. We also have a cloud-based version that is, both of those are computationally quick, and you can analyze samples in as little as 35 seconds. But more importantly, let's dive into these chips. So the three new chips that we have, the first one I'm going to talk about is the Global Screening Array. A lot of folks in this room, that might sound very familiar because MGI is actually based on the version 3 of the Global Screening Array. This new array is pretty similar in content. It has 650,000 markers. It runs on the Infinium workflow, but the biggest difference is the turnaround time on this. So what I was explaining before with the 48 sample chips, it allows us to genotype more samples in a 1-year time span. The workflow is a little bit easier, so it involves new automation. So this will increase the turnaround time, but also decrease the chance for human error. It's very robust, reproducible, and what's really nice about this, and what MGI has actually taken advantage with the version 3, is you can add custom content onto it. So if this array doesn't have markers that are pertinent to your research topic, we are more than willing to work with you. We can add up to 50,000 different markers onto these. But in addition, we also have what we call boosters. I'll go into those a little bit more later, but these boosters have predefined content. This could be, we have multi-disease content, we have carrier screening, pharmacogenomics, cytogenetics. I'm missing a few. There's a psych one, there's a neuro one. We have a bunch of different ones. We're more than happy to give you some of the content to see if it works with your research. But again, if not, custom content is always an option. Jumping into the next one, we have the Global Clinical Research Array. This one was designed to be our most comprehensive one with 1.2 million markers. This one's very important if you're looking at the clinical research aspect. So a lot of these markers, I'll show you in the next slide on what the content involves, but it combines the Global Screening Array with some clinical content that are curated from databases such as ClinVar, NHGRI, GWAS, ACMG, and more. Again, similar to the other array, you can add custom content. You can also add our boosters. But jumping into this one, the content is partly coming from the GSA. It also comes from our GDA, which is called our Global Diversity Array. That one has, I believe, 1.8 million markers, and that has been around for quite a few years at this point. Again, it's coming from databases where we collated some of the markers of interest. We have blood typing markers, clinical updates to it. You can also add the enhanced pharmacogenomics markers, and again, the custom content. So the GCRA and GSA, like I mentioned, we can add customization to it. Here I'm just showing you a small snippet of some of the boosters that we have. So if you look at the third one there, this came from what was previously known as the psych array. I know a lot of researchers at the University of Michigan I've worked with have used the psych array in the past. We have now created a psych booster that can be added on to the GCRA, GSA, as well as other arrays that we have in our portfolio. But the psych booster is really nice if you're looking at some of the psychiatric disorders, especially some of the ones we already talked about today, that were collated based on previous research as markers of interest. Now jumping into my favorite topic. So for context, I actually came out of the University of Michigan and I studied epigenetics. Methylation is one of my favorite topics, so I will quickly go through our new exciting methylation array. So this methylation screening array is one of our most condensed versions of our methylation platform. So if anyone here has ever worked with methylation data, you've probably heard of the EPIC array or EPIC version 2, which is currently out right now. That is an extremely comprehensive, slightly expensive methylation tool. This one is a collaboration with researchers to figure out what content is most important, make it in a more condensed version of the array, make it a little bit cheaper, and then putting it on the new EX platform, you can make it a lot faster. And just to put some context around this, we worked with the Children's Hospital of Philadelphia, 2 collaborators there, and what they did is they bioinformatically pulled a bunch of published research papers and pulled out the clinically relevant methylation CPG sites of interest. They also did the exact same thing, but for sequencing data that was out there, and pulled those points of interest, collated all those together. These are, and I should mention that these are not just research projects that are clinical based. We have environmental exposure ones. We have a bunch of aging clocks that we pulled out, cell type methylation, you name it, they probably looked at it. From this, 53% was pulled from the EPIC array, 43% is brand new content that they pulled. But in total, this array only has 270,000 CPG sites. It does allow more accessibility to researchers for these large biobanks because of the reduced pricing compared to EPIC, but it is a phenomenal resource, and I highly recommend considering this in your research study for multi-omics. But again, like I was mentioning before, the Dragon Array software that we actually have methylation QC for it. You guys are really lucky. You have a phenomenal epigenomics core here that they're actually looking into this as well if there's interest in MSA. But we're having them test out some of this. It sounds like it's going to be very useful, highly streamlined, and works very well with both EPIC as well as the MSA. But in fact, if you're interested in MSA, we actually have a grant going on right now. Unfortunately, I just realized I didn't put the website on this, but if you Google the Illumina Epigenetics Research Grant, you can apply for a little over 1,000 samples to test out on MSA for your project. This is, the due date is October 20th. Okay, and lastly, which is a good segue to Dr. Kim's talk right after mine, is multi-omics sequencing. So many people in this room probably know Illumina is one of the leaders in the sequencing world. The University of Michigan Advanced Genomics Core, as well as Dr. Kim's lab, have invested in Illumina technology for quite some time. The newest sequencing instrument that we've launched is called the NovaSeq X Plus. What's really exciting about this instrument is it's helped reduce the cost of sequencing significantly. And if you've noticed, if you use the Advanced Genomics Core, if you notice within the last year that your cost of sequencing has gone down, it's because of their investment into one of these instruments. It allows for greater accessibility to whole genome, whole exome, whole transcriptome, any ohm, any sequencing, single cell spatial, you name it, we can make it compatible with this instrument. But what I want to put in perspective is how powerful this is. So put this in perspective, the old instrument we called the NovaSeq 6000, still a phenomenal instrument, it's a workhorse, it's great. But what the X Plus gives you is 16 billion more reads. And to put that into context, that is 40 more whole genome and whole transcriptome samples at a 43% less cost. And not only that, is it 2 times faster and it's 3 times more accurate. Put it into more perspective, what can 16 billion reads give you? That's 320 more samples of bulk whole transcriptome sequencing, or 320 more samples of ATAC or bulk ATAC sequencing, or better topic, single cell is pretty popular here at the University of Michigan. That's 330,000 more cells for single cell ATAC sequencing with gene expression profiling. Again, all faster, more accurate, and lower cost. But again, let's put this in a kind of conceptual matter. So 16 million more reads. Let's say you want to do a project with 7,500 human whole genomes. Right now, that's about 113 25B or 25 billion flow cells on the NovaSeq X. That is roughly just a sequencing cost of $1.8 million. Previously, on the other instrument, that would have cost $4.7 million with 300 S4 flow cells. So as researchers like yourself start to invest in sequencing, genotyping, it pushes our company to innovate and make things faster, more accurate, and more accessible so you guys can make the discoveries that you make today. Again, I want to thank you for this very quick brief talk. Like I said, I'm on the research side of things, so here's my email address. You can take a picture. Or if you're on the clinical side, please reach out to Jeff. Either way, either of us will help you out. Yeah.
So our last talk is from Annette King, and she will talk about the technical aspects of genotyping.
All right, everyone. Well, last stretch. Hang in there. I did like to introduce myself. I am Annette Kim. I am the director of the Diagnostic Genetics and Genomics Division within the Department of Pathology. We are your CLIA laboratory. Anything you want done under CLIA for testing purposes, that is us. All right. I'd like to give a little history. My division originally was 3 different laboratories that were spatially separated and actually located within 2 separate departments. We all were unified in a single department as of November 2022. I came in July of 2023, and we established a completely new leadership organization with 5 successful faculty recruits, 3 of whom are in informatics, and we are in the process of recruiting several more. We held a retreat last October with successful rebranding and unification of all 3 laboratories under a common vision, which is to bring state-of-the-art molecular diagnostics to Michigan medicine. Simple enough. I'd just briefly like to make you familiarize you with some of the testing that we already do, and then we'll get into what our plans are. We already do both constitutional and oncology karyotype fluorescent in situ hybridization and chromosomal microarrays using some of the iScans that you just heard about. In our germline laboratory, we do a number of single gene testing, and we also have already a clinical exome panel that we use. We are doing exome slices from that clinical exome panel, but we do already broad NGS sequencing within the germline laboratory. And then within the molecular diagnostics laboratory, we not only have a wide number of single gene assays, we do methylation chromosomal microarrays already for clinical purposes. And then we have 3 separate NGS panels that we do right now, one for the myeloid, one for solid tumors, and one specifically on RNA for fusions in solid tumors. But we are building a lot more from there. We're building for scale. So we have brought on Hamilton liquid handlers for high throughput efficiency in the laboratory. We have the world's most advanced sequencer that you just heard about. It's a NovaSeq X Plus. And actually we are now looking to purchase a second one. And we have faculty experts in genetic and genomic analysis and CLIA, and in the future, sadly for us, also probably FDA regulation as well. Shown up at top, you can see this is probably about half of our sign-out faculty right here. These are the people who really get you the results that you need. We have big plans in each of the laboratories, and I'm going to focus in on the sequencing stuff, but I just want to mention all of it. So within our oncology laboratory, we are bringing on a very rapid NGS solid tumor panel called the Oncomine Precision Assay. And then we are bringing on a version of MCTP's MyOncoSeq. We're kind of roughly calling it DGG OncoSeq. And I'll talk a little bit more about that in a second. Within our germline laboratory, we are bringing on whole genome sequencing. We've vetted or batted around the idea of a sort of an exome sequencing and then sliding into genome. We're jumping straight to whole genome sequencing in the clinical setting. We're going to initially start out reporting our exome slices, but moving towards whole exome reporting and whole genome reporting, but it's all on a whole genome platform. And then finally, within our cytogenetics lab, we are also bringing on optical genome mapping, which is a fascinating technology for structural variants and copy number variants, but it's not sequencing, so I'm not talking to you about it today. I'd like to first go into the DGG OncoSeq because you'll see that it ties into everything that we're talking about with whole genome sequencing. So we looked under the hood of the MyOncoSeq assay that was developed within MCTP. It was revolutionary for its time. It was originally brought on in 2013. At the time, it was probably close to 2,000 genes, paired tumor normal whole transcriptome, and it was designed to be very flexible for research purposes. However, we are highly regulated. That's what is required for CLIA. And so when we looked under the hood, we discovered that the MyOncoSeq wet bench work is very complex and difficult to scale because it was, again, built for flexibility, similarly with the bioinformatics. And so as we thought about bringing this assay on in the clinical laboratories, we ended up swapping out every single part. So we're doing a completely different library preparation. Again, ours is also going to be automated on the Hamilton liquid handlers. We've combined with a number of academic institutions across the United States to purchase in bulk probes. So we're using a completely different probe set. We're probably going to use a different exome baiting strategy for our whole transcriptome. And we have a brand new modular pipeline that I'm just going to briefly mention as well. This whole process is going to be optimized for robust performance, even for tiny, tiny small biopsies and low quality FFPE specimens. And we will be reporting on mutations, mutation signatures, TMB, MSI, CNV, and gene fusions. Our current panel is being designed to be about 1,100 gene targets. It includes cancer germline predisposition. It includes cancer PGX, so the DPYD, the UGTA, all of that's on this panel. All right, anything you could possibly need for decision making about cancer therapeutics is on here. And the coverage we're targeting around at least a minimum of 500x. We do DNA, tumor, and normal. And so for that initial process, the whole thing's going to be automated. And then, of course, we're going to run them on our NovaSeq sequencers. There's also the possibility of getting additional Hamiltons and automating the second day process as well. When thinking about a pipeline, I wanted to make sure it was modular so that any innovations that came about through the research that everyone here is doing, if a new signature is identified, something, we can just pop in a new module to our pipeline and concatenate it in. And so we developed, my colleague Marcin Cieslak, actually not we, Marcin developed his turnkey precision oncology or TPO pipeline that allows input and different library preps, different sequencing strategies, different results reporting. And so for instance, for our DGG OncoSeq, it would look something like this, for instance. He has done benchmarking against the Broad, Gady Getz's lab there, and TPO's performance is excellent with far fewer false negatives and high concordance. And then we have an entire sort of informatic ecosystem that we are building that allows CLIA return of results, including cloud analysis. And so we are building a ecosystem, including a data lake with a lot of different types of data being stored, copy number, signatures, cytogenetics, mutation signatures, all within this data lake. And then we're going to allow for rapid retrieval of data on individual patients or cohorts. So with that, as sort of the underpinnings of what we're building in the oncology lab, let's move now to what we're doing with the NovaSeq in the germline laboratory. Like I said, we contemplated long and hard about the relative benefits of going to exome sequencing first and then migrating to genome. And we finally said, pardon my French, screw it. Let's just go straight to genome, all right? It's the wave of the future. It provides the most ample opportunities for research, and it's going to, it actually has some very significant technical advantages that are going to facilitate our turnaround time. So compared to exome sequencing, which covers about 1.5% of the genome, genome sequencing covers about 92% of the genome, both coding and non-coding regions. The reason that's not 100% is because there are some difficult to sequence areas. We are using a library prep that is going to be PCR free, and I'll show you some of the advantages of that. I probably should have highlighted and bolded that one as well. The library prep time, instead of being 2 days, is going to be a half day, which it really is going to help enable our ability to offer rapid whole genomes. Coverage is usually typically less. It's more like 30 to 40x. We can have mitochondrial coverage. We will have very good coverage even in GC-rich regions, so less bias. We will have better CNV resolution. We can detect structural variants. Is much better at repeat expansions, which are, again, difficult to sequence areas, and the diagnostic yield is higher than for exome sequencing, although we can pick up about 85% of what we want by exome sequencing from the clinical perspective. And then, of course, new genotype-phenotype correlations is enabled better by whole genome sequencing. So whole genome sequencing definitely has better, more uniform coverage than whole exome sequencing. Exomes shown on top, this is a view of IGV, and exome is shown on top, and on the very top bit you can see the coverage bar, and you can see that sometimes the coverage bar is rather low, sometimes it's high, it tails off on either side of the exons. Sometimes there's a trough as shown on the, does this work here? So there's sometimes a trough even in the middle of an exon in coverage, whereas whole genome sequencing has much, much more uniform coverage. High GC regions are extremely problematic for sequencing, and you can see how in whole exome sequencing, there is phenomenal poop out of our coverage right here in the middle of this high GC rich region, and that is obviated by the whole genome PCR-free process that we're looking for, and this is very important for some very clinically relevant repeat regions. Turnaround time. So shown on the top in green is whole exome sequencing workflow, and shown in purple on the bottom is the PCR-free whole genome process that we are planning to utilize. There is, I think the money is all right here. Whole exome sequencing, depending on your hybridization and how many PCR steps you have, it's 1 to 3 days of library preparation time, and in whole genome sequencing, it is 90 minutes. And since we're going to be using this on the Hamilton, that is 90 minutes of with the robot doing the pipetting. And then finally, sequencing and reporting. And so we can use TPO to now mix and match a different subset of modules and use this for peripheral blood and stored DNA in a PCR-free library preparation. Or, as was mentioned previously, there is online Dragon that comes with the NovaSeq X Pluses. So we can actually do our initial processing and alignment on the NovaSeq itself. And so this is, again, just a nice shot of our happy NovaSeq, NovaSeq number 1. We're in a naming process right now. The name we'll update you on that in a second, probably by end of next week. So it turns out size matters. So this is where I think we really get into the nuts and bolts, and there's a lot of math that goes behind what's simplified on this screen here, but there are 3 different size flow cells that can be run on the NovaSeq X Plus. One is the 1.5B, there's a 10B, and the 25B, B being billion reads, right? You can see what the data output looks like. We are shooting for 40x genomes, not 30x genomes, because clinically that's what we think would be best for our patients. And so on a 25B flow cell, we can do 48 40x genomes. The list cost of a flow cell, a 25B flow cell, is $16,000. So when you do that, the cost per genome is $333. Other laboratory costs, including the library prep kit itself, the indices, the tech time, the other reagents and consumables, all adds up to about $58, and the data storage per year per genome, so the per year is the sticking point here, is about $8. So giving us a total cost for the genome of close to $400 on a 25B flow cell. However, clinically, right this second, we can fill one 10B flow cell maybe every other week, or a couple of 1.5B flow cells. But you can see what that does to the cost per genome. If we're working off of 1.5B flow cells in order to increase the turnaround time decrease the turnaround times for our patients, we're talking $1,200 for a genome. Whereas if we can get down to using a 25B flow cell, it's $333. That brings me, this is where, really having a volume in order to fill 25B flow cells, ideally multiple per week, gives us both the turnaround time that we want and the decreased cost that we want. And with my Illumina colleagues here in the audience, I'm not allowed to give a number exactly yet because it's still pending approval from the Illumina higher ups, but I think we can get this down to below $300. For the entire thing, from nuts to bolts. So again, this would be a very large collaboration with Illumina. They would be partnering with us in order to enable a very rapid and inexpensive genome. One idea is that we would do all of the sequencing for MGI under CLIA, the CLIA umbrella, and give the data directly to MGI. We have a couple options. We can give fast queues, or we could run it through the pipeline and give BAMs and VCFs. And I think that's still a discussion that we need to have. But we can give all of that data directly to MGI. And then when you decide that you need a CLIA return of results because there's something actionable that you would like to put in the EMR, we can run it through the rest of our tertiary analysis pipeline and sign it out, all under CLIA. This is just a summary of how a collaboration between the Michigan Genomics Initiative and the Diagnostic Genetics and Genomics Division would dramatically impact both the research and the clinical missions here at the University of Michigan. So one thing that this does, it keeps all of the data in-house, right? So it protects Michigan Medicine from third-party consumers of data. We can then elect to share that data in a limited fashion through a number of these consortia for which then Michigan Medicine folks would be the PIs, right? But it protects all of that data because despite the fact that genomic testing results are not considered PHI, by definition, if we're doing whole genomes, it's identifiable, right? This supports the University of Michigan and Michigan Medicine research more broadly, and it will increase prestige to Michigan Medicine and University of Michigan through research and innovation. At the same time, it decreases the cost for our patient genomes. There will be faster return of results for our patients, and there will be increased prestige to Michigan Medicine because we will then be able to participate in things like the Undiagnosed Disease Network or UDN. We can advertise that we can perform rapid genomes, et cetera. And so just as a final slide, just very conceptually not drawn to scale, because the Michigan 100,000 compared to our, let's say 5,000, 6,000 samples a year doesn't quite compare, but it ends up that the timing would be perfect because it would basically allow us maybe to have sort of a gradual sort of slow start to our MGI uptake, but then we could do massive MGI sequencing while we bring on all of these clinical assays, and then we are currently sending out whole genomes, whole exomes, and some of our cancer panels. We would be bringing all of that testing in-house with the availability of our panels, and so our testing volume clinically would go up as the MGI volume returns down to the steady state after we get through the retrospective cohort. Important shout out here to the Advanced Genomics Core and Tom Wilson's group, because we can't do it all. And they also have a lovely NovaSeq X Plus, and we would be utilizing some of their bandwidth as well. Just please note that those would not be under CLIA, so there would potentially be resequencing or retesting required if something came out of those. And with that, I would just like to thank all the people I've worked with, some of my colleagues who helped me provide the slides, and of course, the incredibly fruitful discussions we've been having both with MGI and Illumina. And with that, I will take questions.